Okay, this is Maths 2020. I think it's lecture number 33. Last time we finished section 11.2. Today we shall cover section 11.3, which is called the integral test. Okay, so I want to sort of recall what we did last time, just briefly. We did section 11.2, and that was about the divergence test for a series. What did that say? It says that if the limit of the terms at a sub n of a series do not go to zero, if this is not zero, then the series summation a sub n diverges. So I want to sort of re-emphasize the following. If the limit happens to be zero, this tells you nothing. The series might diverge or converge. It tells you nothing. The test is not valuable in that case. So the test is useless when this happens. It's only useful if the limit is not zero. Okay, so let's move on to section 11.3, which is called the integral test. I want to motivate it in the following way. So suppose we look at the following example, summation n equals 1 to infinity of 1 over n squared. Now, up until now, we have no methods to determine whether this series diverges or converges. If you apply the divergence test, 1 over n squared tends to 0, so it tells you nothing, the test. However, we can still consider the following. So let's consider the following graph of the function y equals 1 over x squared, right? So that's the following function. So it looks like this. It's a curve. Now, if we plot the integer points on that curve, 1, 2, 3, we get these points here. And the sum of the series is given by the areas of these rectangles I'm drawing in. Etc. So let me fill in the rectangles. And so the sum of the series, if it converges, is less than or equal to the area under the entire curve, right? So so if the area of the curve is finite, which it is, we saw that back in improper integrals way back when, it should be true that the sum of the series is finite. That is, the series should be converging. So let me state the integral test, okay? So let's assume, so here's the statement. Assume f of x is greater than or equal to 0, is continuous, and it's decreasing. And this is on the interval from 1 to infinity. We're going to look at it, but actually it's going to work on every interval, this statement. And let's set a sub n equal to the value of the function at n. Okay, so then the statement is then sigma a sub n converges, that is, the series converges, if and only if the integral from 1 to infinity f of x, it's not an if and only if, it's an if. So, oh, actually it's an if and only if. Let me restate it, what I wanted to say. I should have meant it in the other direction. So if the integral is finite, that is, it converges, then the series summation a sub n converges. We also have the contrapositive version of this. The contrapositive version would be if summation a sub n does not converge, that it diverges, then the integral of f of x dx diverges as well. But that's not useful for, that formulation is less useful for series. Okay, so this is what we want to look at, this statement here. This is going to be useful to us. Okay, so it does not say, though, what the series converges to. It just says the series converges to something. That's very important because it's telling you the integral test is really, in the end, a test that's about, it's a qualitative test. It doesn't tell you what the series, the sum of the series actually is. Okay. So let me make some remarks on the next slide. I made the following remark already. It's enough that f of x be greater than or equal to 0, continuous, and decreasing on any interval to infinity, on some interval from a to infinity. That's enough. You don't need it on from 1 to infinity. You could have it on the interval from 25 to infinity, and that's enough. Okay, the second statement is that the integral test is qualitative. It cannot tell you what the series converges to. If it converges. Okay, so that's, I want to just do some examples now. So let's go back to our example. Summation 1 over n squared, n goes from 1 to infinity. So now the function f of x equals 1 over x squared is continuous. It is non-negative and it's decreasing on the interval from 1 to infinity. So we're good. So therefore, we can compute the integral from 1 to infinity of 1 over x squared dx. And we know that that will converge by what we did in improper, when we considered improper integrals. So this converges. So therefore, that we conclude summation 1 over n squared, n goes from 1 to infinity, converges. So we're good. Okay, so that's the first example. The second example is the P series, the so-called P series. That's summation 1 over n to the P. And P goes, n goes from 1 to infinity. Here P is any real number. Okay, so there are three cases to consider. There's several cases to consider. P is bigger than 1 as an example. Well, then we're going to compare it to f of x equals 1 over x to the p, which is indeed decreasing, continuous on the interval in question 1 to infinity. And we know that the integral from 1 to infinity of 1 over x to the p dx converges if p is bigger than 1. So that means that a summation 1 over n to the p converges in this case, if p is bigger than 1. So that's case p bigger than 1. The case p equals 1, or actually the case p is, the case p is, so the case 0 is less than p is less than 1 is next. We know that the integral in that case, or actually less than or equal to 1 will work here, of 1 over x to the p dx diverges. So that's not going to help you. However, so the integral test will not work. I have to go back, I realize, and I misstated the integral test. I apologize. So let me go back to the previous slide. No, that wasn't the previous slide. I want to go to this slide. Okay, so what I should have said is this, right? So let me erase, let me apply the eraser to what's over here. This is not so interesting anyway. I want to say is this, is that the other part of the test, which I did not state, is that if the integral actually diverges, then the series also diverges. So it's an if and only if. So I blew this statement actually. Sorry. So that's the companion statement. So it's an if and only if. You could put an if and only if here. Okay. So let's go back to what we were doing with the p series. So if 0 is so it is not true the integral test doesn't work. Since the integral diverges in this case, the series diverges by the integral test in this case. Now what happens when p is equal to 0? You can't talk about that, but p less than 0, well, actually p equals 0 is stupid. That's the case summation 1 over and over and over, adding 1 together, this diverges. And p less than 0, look what happens there. Well, 1 over n to the p can be rewritten as n to the minus p, and now n to the minus p is a number greater than 0. And if you take the limit as n goes to infinity in that case, this does not go to 0, right? It converges to infinity. So the divergence test applies. So when p is less than 0, it diverges. So let me summarize the solution that we got. So the p series converges if p is bigger than 1 and diverges otherwise. Okay, and this is something to remember going forward because this is used over and over and over again. All right. Here's another example to consider. Summation n goes from 1 to infinity of ln of n over n. Now, we can't use the divergence test here because ln of x over x by L'Hopital's rule, the limit, L'Hopital's rule says the limit as x goes to infinity of ln of x over x is the same as the limit as x goes to infinity of 1 over x over 1, and this is 0. So the divergence test fails. Doesn't tell you anything. However, we can consider the function f of x equals ln of x over x. And if we know, I want to apply the integral test, so we need to know if the function is non-negative. It is. That's easy to check on the interval, 1 to infinity. Is it continuous? Yes, it's continuous, but is it decreasing? So we have to check if it's decreasing. So that's a question mark. Well, how can we do that? We could take the derivative. The derivative is f prime of x. By the quotient rule, it's x times 1 over x minus ln of x times 1 over x squared, which is 1 minus ln of x over x squared. Now, if x is bigger than 1, if x is bigger than e, well, strictly bigger than e, then f prime of x is negative, because ln of e is 1, you got 0, and then any value bigger than e, ln is an increasing function. So therefore, since f prime of x is negative, it follows that f prime of x is decreasing, f of x is decreasing on the interval from e to infinity, and that's enough, I said, for the integral test. Okay, so let's apply the integral test. So let's consider the integral from 1 to infinity of ln of x over x dx. Well, this, we can set u equal to ln of x, then du, I'm doing a substitution, is dx over x. There should be an x here. So so the limits of integration change from 0 to infinity of u du, and this is u squared over 2 evaluated from 0 to infinity. Being slightly sloppy, the way I wrote my limits of integration, that's okay, but this is plus infinity. So this diverges, this integral. So this series by the integral test summation ln of n over n diverges, which is what we wanted to know. Okay, let's try another example. Well, let's talk about something else. Okay, so what I'd like to talk about is two series, the harmonic series and the series 1 over n squared. In order for me to talk about what I want to talk about now, I have to go to the web. So there are calculators online which will sum up series for you, at least a finite number of terms, right, in a series. So I want to show you something interesting here. Okay, so let me change the sharing of the screen. Okay, so I've gone to Wolfram Alpha. There's a widget on Wolfram Alpha which will sum up series, so up to an arbitrary number of terms that you can put in. So I'm looking at the harmonic series here. Now we know the harmonic series diverges, but let's see how it diverges. Let's see how quickly it diverges. So we can sum up 1 to 10. What do we get? So that's the first n terms. We get this fraction. That doesn't look too good. Let's try to, I want to get a decimal. So let's see what happens. We'll do the first 100 terms. Oh, I don't know why it's doing it this way. It should be, it's giving me fractions when it should be giving me decimals. Wow. Yeah, I guess you have to go to a large value, number of terms to get decimals to see where you are. So here is, what is it? It's a million terms. You get 14.4 approximately as the sum. Now what if we go to a billion terms? Let's see what we get. So let's see how much it changes. The first billion terms gives me 21.3. It hasn't moved that much. What about the first trillion terms? 28.2. See, it's not diverging very quickly. If I keep going, I put 3 more zeros. What do I get? 35. It doesn't go up that quickly. It diverges extremely slowly. 42. I'm really, this is a huge number and it's adding them all up. And now it just sort of gives me an error because I've gone too much. Let's see if I take, let's see how high I can go here. Yep, it's giving me error now. I broke the calculational ability of the machine here. So anyway, this is what you get for the harmonic series. Let's try our series 1 over n squared. And let's calculate the first million terms of that. We know it converges. So it looks like 1.64493. What if we go to the first billion terms? It doesn't change. Trillion terms. It just stays stable. Now this number, 1.64493, is actually, turns out this is a well-known number. And let me go back to my other sharing. I'm going to stop sharing here and go back to the whiteboard. So here is a fact which we may or may not be able to, I might not be able to show you why it's true until late. I won't tell you until at the end of the section, at the end of the chapter, I should say. So here's a fact which has been known for several hundred years. It's due to a mathematician by the name of Euler. And it's this: if I take the sum of 1 over n squared, so n equals 1 to infinity. So that's, of course, then that's pi squared over 6. So the number pi squared over 6 was that number, was an approximation to that number. In other words, if I want to calculate up, this gives you a way of calculating pi very, very simply, because you can add 1 over n squared. So this is the series, of course, 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc. And that's going to add up to pi squared over 6. So that's kind of amazing, I think. Yeah, so that's it for today. We'll continue next time with other tests for determining whether series actually converge or diverge.